had talked about a normal distribution, okay? And just as a reminder, let's see, I'll go back up here. Just as a reminder, a normal distribution, we've heard about these, we've talked about these since we were in high school or middle school or certainly college, as we talked about a bell-shaped curve. If we've got something that follows a normal distribution, it has some really nice properties statistically for us. And if we make the assumption that returns are normally distributed, then right in the middle of this distribution is our mean. I'll call it R bar. Put a little bar over the R. The R stands for return. So that's our mean, our average, arithmetic mean. And again, if we are evaluating and examining variables, in this case it's returns, that are normally distributed, then the properties that I talk about that are kind of favorable is the fact that approximately 68%, specifically it's 68.26, but I'm just lazy, I'm going to put about 68% of the area under the curve falls within one standard deviation of the mean. If we go 2 standard deviations away from the mean. So that's minus 2 sigma and plus 2 sigma. Sigma is the symbol for standard deviation. Then it's about 95% of the area under the curve. I'm going to change colors. I meant to do that a minute ago. 3 standard deviations and minus 3 sigma standard deviation. Almost 100%. It's 99.74 actually, but I'm going to still put about 99%. So those are some pretty favorable qualities because it allows us to forecast, really, maybe predict, if possible, what the returns might be. For instance, if we have a mean of 12% and a standard deviation of 8%. I'll put 12 right here. That's the mean. If I go 1 standard deviation away, 12 plus 8 takes me to 20, and 12 minus 8 takes me to 4. And so I could say then that, next period, there's a 68% probability that my return is going to fall somewhere between 4 and 20%. Okay. So anyway, that's our normal distribution. And again, when we're doing some empirical research and working with returns, it's nice to assume normal distribution. In a lot of research, they assume returns are normally distributed. They're not always perfectly distributed, but again, if something follows a normal distribution, there's some favorable properties. So what are some of the challenges then to normal distributions? I mean, if returns aren't always normally distributed, then maybe what properties or what characteristics do we face? And the first one we see here is called skewness. Okay, so we can see these 2 distributions before you. Certainly they're not computer generated as I hand drew these. Both of these distributions show skewness. Okay, the one on the left hand side, this would be a positively skewed distribution. Positively skewed. Now what we can see here, we've got maybe some really positive values out here someplace that are stretching this distribution out. Some extreme positive numbers or some extreme positive observations that then cause us not to be normally distributed. If we go back to our normal distribution, and I realize this isn't very impressive looking distribution, I drew another one down here. The one over here in red, okay, the one on the right. Let's assume that's a normal distribution. You can see we're symmetric about the mean. Half of the values on a normal distribution fall to the right of the middle, right of the mean, and half the values fall to the left. That's not the case with skewness. We can see there are more extreme values in the case of a positively skewed distribution and a lot more there are some extreme negative values for negatively skewed distributions. Well, what's kind of important here, some of the challenges to normality relates to those characteristics that we just talked about, standard deviation. If you've got a distribution that's positively skewed, you'll see in the textbook the standard deviation, well, let's see, what do they say here? Standard deviation overestimates risk. These distributions, or these returns out here, there's not that many of them, but there's several that are way on out here, and what that's going to do, those are pretty significant deviations from the average. And so what that's going to do is that's actually going to increase your standard deviation. If you'll look at your distribution, now I wish I had a pointer. I don't really have a good pointer. I think maybe you're seeing this on here. But if you'll notice here, most of our values are still in the left-hand side of this distribution. There's only a handful of these smaller or these large numbers that are stretching us out here. So still, most of our values are going to fall relatively close, let's say, to the mean. But because we've got these extreme values here, it's going to increase the standard deviation. Remember, standard deviation is a measure of risk. So these variables out here are causing our standard deviation to be higher, and it's going to overestimate the risk. When we evaluate that standard deviation and we see how high it is, we might mistakenly think, wow, that's a really, really risky thing, risky asset. And it's not, because these returns out here that are extreme, there's not that many of them. And by the way, they're very positive. Which one of you would be unhappy if you had, maybe you were expecting to earn 12% this year, but you earned 50% this year, right? That's an extreme positive value, and you'd be elated. And yet, it actually would increase the standard deviation because you had that huge positive return. So when you have these extreme positive values, standard deviation really isn't the best measure of risk because it's going to overestimate. On the other hand, what if we had a negatively skewed asset? Well, a negatively skewed asset actually is going to underestimate the risk. You've just got a few of these extreme low values out here, and most of the returns, again, it looks like over here are positive, but it does increase the estimate of volatility. But when the distribution is negatively skewed, standard deviation underestimates that risk. So those are two issues that we have to be concerned about. If we've got normal distribution, everything's great because half of the area under the curve falls to the right and half of the area under the curve falls to the left. All right? But if it's a skewed distribution, the use of standard deviation as a measure of risk really kind of becomes suspect. We're going to see some alternative measures of risk here in a moment after we talk about one more challenge to normality. And that last challenge is called kurtosis. All right. Let's see. It was really hard for me. I was trying to draw kurtosis, or a distribution that exhibits kurtosis. I want you to look at these two distributions. The one on the right, I'm going to say is normal. I tried to make a normal distribution. The one on the left, I'm going to say exhibits some measure of kurtosis. Okay? And if you'll notice here, it's hard to notice. It's hard to see. But I want you to look at the tails of my normal distribution over here. Look at the tails. So here, and when I'm talking about tails, I'm talking about this area here underneath, in the extremes. So this is showing us that there's only a few outliers, a few that are in the far end, a few observations that are in the tails. Okay. If there were more observations in the tails, our tails would be fatter. And if you'll notice, that's what we have with kurtosis. Look at the distance here in our tails versus here. I'll try to change the color. The distance isn't as high. There's not as much area in the tails as there is over here. Look how much area is in the tails on this side. So this distribution on the left exhibits kurtosis. Okay, and that means that there are more deviations that are extreme. Not necessarily further out, but there's more of them, and that's what this area under the curve, the fatness, is showing us, is that there's more observations that are deviating from the mean on the extreme levels, as opposed to with our normal distribution. Yeah, there were some, but there weren't very many that were extreme values. And so that changes the distribution. When you have fat tails, and that's what we're seeing here, fat tails, then that's showing us a measure of kurtosis. If you'll notice also, it makes our distribution a little skinnier, doesn't it? Because if you'll notice on our normal distribution over here, we've got this nice bell-shaped curve, right? But on our kurtosis, we've got a skinnier distribution. There's less values that are in the middle near the distribution and more of them that are actually in the curve. I'm sorry, that are in the tails. So normality, yep, we like normal distributions because there's some great characteristics. We've got the mean right in the middle. If a distribution is normal, half the observations fall to the right of the mean, half the observations fall to the left of the mean. We know that if a distribution is normally distributed, if the returns or variables are normally distributed, then approximately 68% of the area under the curve falls within one standard deviation. Approximately 95% falls within two standard deviations, and like 99.76% falls within three standard deviations. Those are some great characteristics that only apply to a normal distribution. Okay, so since we've now determined that standard deviation is a great measure of risk if we have normally distributed variables, observations, we need to come up with some other variables, maybe some other measures of risk that might be appropriate if we don't have a normal distribution, or if we decide for some reason standard deviation is not the best measure. So I'm going to give you four of them. Three of them are discussed in your textbook. The fourth, I'm going to actually start with that one. So there's a measure called semivariance that we're going to talk about. But before we do that, let me give you an example. Let's say that we have the following 10 returns. We had a 12% return, -7, 10, 7, 9, 15, 12, 2, 8, and 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I did this earlier. I hope I still did it correctly, but let me calculate the mean real quick. 12 minus 7 plus 10 plus 7 plus 9, 15 plus 12. Okay, good. The sum, when we sum all these, it's 87. And since there are 10 variables, 87 divided by 10, the average is 8.7. Now, if I wanted to calculate the standard deviation, we know how we would do that. I'll show you, and then I'll probably erase it because I'll need my space. But remember, our formula for standard deviation says take each one of the returns, 12. We'll start with that one. Minus the average, which is 8.7, and square it. And then take the next return, which is -7, minus the mean, 8.7, and square it. And then the next one, 10 minus 8.7 squared. We do that for each one of them. The last one would be 19 minus 8.7 squared. When I do that, I divide all of that by the number of observations. There were 9 of them. I'm sorry, there were 10. And that gives me my variance. And then if I take the square root of that, that gives me my standard deviation. So we could easily calculate standard deviation. By the way, your calculators, if you have a financial calculator especially, it'll knock this out in seconds. As fast as you can enter in 12 and -7, 10, and so forth. It'll take you like 15 seconds total to calculate standard deviation. Now, so we could calculate standard deviation. But I want to point out a couple of things here. I want you to look at this number right there, 19. That's the highest number. 15 was also good. Look at all these. If the average was 8.7, don't you imagine when you made a 19% return one period, you would have been really happy? Or when you made a 15% return, you were really happy, right? So what we've got here are some really positive returns. And if you remember, we said earlier, if you've got positive returns, some extreme values, you're probably going to have a positively skewed distribution. And if you remember, we said it overestimates the risk, and it does. Because that 19% and that 15%, here's the 19, the 15's in here somewhere, but look, that's a pretty significant deviation from the mean. But it's a positive deviation from the mean. It was good news if that was your investment. My point is that standard deviation is still going to take that into account, and it's going to result in a higher standard deviation, which implies that it's more risk. When in fact, I don't know, that was really some good volatility. So there are 2 alternative measures here that we're going to talk about. One of them is called semivariance. What we're going to do with semivariance is we're only going to we're not going to use all 10 of our returns here when we calculate a measure of risk. We're only going to use those returns that were less than the average, less than the mean. Okay, so let me copy this over here. Oop, that's not what I meant to do. Come on. All right. So for semivariance, we look at each one of these returns and we say, okay, which ones were, what we're going to do is only consider the ones that were below the mean. Oh, as it turns out, I don't think I have the best example here. I was thinking I was doing something else. But with semivariance, we're going to basically ignore the returns that are greater than the mean. Okay, so semivariance is going to consider only those returns that are less than the average. Basically, it ignores the returns that are greater than the average. So whereas standard deviation would use all of those returns, semivariance doesn't use all of the returns to calculate some measure of risk. It only includes the ones that are less than the average. So I didn't give you a very good example here. I did it backwards. I just created another one. So, but let's run through this one anyway. Semivariance, since the average is 8.7, it would say, well, we're not going to include the 19 because that was good volatility. Right? Actually, we're not going to include the 12 or the 15 or the 9 either because those were higher than the averages. The 10 and the 12 were higher than the average. So we would use the remaining values, the -7, the +7, the 2, and the 8, to calculate some measure of deviation. Semivariance only looks at the returns that fell below the mean, because that would be negative volatility. The returns that were greater than the mean are really positive volatility. I tried to create another example here real quick. Let's see if this one makes any more sense. Let's say we had a 22% over time, a 7, that's -7, 4, +7, 6, 15, 8, 3, 8, and 19. So let me add these together. I've got 22 minus 7. Let's see, I'll add 11, add 21, add 11, add 27. All right, I'm going to do that one more time because it's not what I came up with a minute ago. 7 minus 4 plus 7 plus 6 plus 15 plus 8 plus 3 plus... Okay, well, that gives me an 85. So the sum here is 85. Since there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the average is going to be 8.5. So if we were looking at semivariance, semivariance is going to ignore any of the returns that were greater than the average. So semivariance is going to say, well, don't include the 22% because that was good volatility. Don't include the 15%. That was good volatility. That was a positive return. Don't include the 19% because that's good volatility. So I'm not going to ask you to calculate semivariance, but I want you to recognize that semivariance is a measure of risk. In fact, it's really a truer measure of risk than standard deviation. Standard deviation considers all of the returns, including these awesome positive returns. Semivariance, on the other hand, is sometimes referred to as a good measure of downside risk because it only looks at the returns that were down, that were less than the average. Okay, that's the one that your book does not talk about. Okay, your book does talk about another measure of risk called the lower partial standard deviation. It's actually similar to semivariance, so lower partial standard deviation. Let's see here. So to calculate the lower partial standard deviation, we need another return to consider, and it's the risk-free rate. Okay, it's the risk-free rate. And so the lower partial standard deviation is going to calculate a measure of variation, a measure of risk, but it's not going to use all the returns either. Right? Standard deviation uses all the returns. Semivariance doesn't use all the returns. It only uses the returns that are less than the average. The lower partial standard deviation only uses the returns that are less than the risk-free rate. So I'm going to put returns less than some kind of risk-free rate that you could earn, for instance, the rate that you could earn on a treasury bill. Okay? So what if we said, let's say the risk-free rate is equal to 5%. Well, we're only going to include, if we're calculating lower partial standard deviation, we're not going to use all 10 returns either. We're only going to use the returns that are less than, in this case, 5%. So we would ignore the 22% because that's obviously higher than 5%. But we would include the -7. We would include the 4. We would not include the 7 or the 6 or the 15 or the 8. We would include the 3 because that's less than 5. So the lower partial standard deviation is looking at, only the returns that are less than the risk-free rate. So two additional measures of risk compared to standard deviation. Remember, I'll say it again, standard deviation looks at all of the returns. Semivariance looks at only the returns that are less than the average, and then calculates a measure of risk from that. And the lower partial standard deviation doesn't look at all the returns either. It only includes and evaluates the returns that were less than the risk-free rate. The last two measures of risk discussed in your textbook, they're kind of close. They're kind of similar. One is called the value at risk, and the other is called the expected shortfall. So the idea with the value at risk is you're going to establish, what is the risk level, let's say at 5%. What's my 5% risk level? What's my 10%? What's my 7% risk level? And so really what you're going to do is you're going to rank the returns from highest to lowest. Now over here, in this previous example, you see these returns that occurred over a time period? Well, those clearly are not ranked from highest to lowest, but we could have done that. It would have been the 22%, then 19, 15, looks like 8, 8, 7, 6, and so forth. We could rank them from highest to lowest. So that's what we're going to do. We're going to rank all of the returns, highest to lowest. And so then, if you wanted to have for instance, the 5% value at risk, you'd go to the bottom and you'd take the 5% value. It would be real easy if you had 100 returns and you wanted the 5% value at risk. You'd rank them from highest to lowest, and you'd go down to the bottom and count up 5. You'd want the 5th worst. That's what the value at risk is at 5%. If you want 5% value at risk, that means 95%. You want the value at which 95% of the returns are actually higher than that. So your book gives you an example, and it says, why don't we assume there were 84 total returns. 84 total returns. And so we're going to rank them from the highest all the way to the lowest. Okay? There were 84 returns. And the last 5 were, in order, negative 25.03. So we got negative, didn't we? Then it got worse than that. 25.69 negative. Negative 33.49. Negative 41.03. And negative 45.64%. And what we're looking for is the 5% value at risk. Well, again, if we had exactly 100 returns, it would be easy, because we would count from the bottom and we go, there's the worst, and then we go 1, 2, 3, 4, 5. This would have been the 5th worst, and that would be our answer. But we don't have 100 returns, right? We've got 84 returns. And so if we take 5% of 84, 0.05 times 84, what we're looking for is the return that would fall at position 4.2. So it's going to be somewhere between the 4th and the 5th. 1, 2, 3, here's the 4th, here's the 5th, so it's going to fall somewhere between those two. And so we have to find that value. We have to interpolate between that value. What we know is that it's going to be at least negative 25.69, because that's the 4th period. That's the 4th observation, rather. And then we have to interpolate. It's going to be somewhere between the 4th and the 5th. So it's going to be 0.2 of the difference between those two. If we take 25.69 minus 25.03, basically we're seeing the difference there. 25.69. Those two differ by 0.66. So we want 20% of that difference. So that should be negative 25.69 plus 0.132. And that gives me negative 25.558. So if you'll notice, that falls between here, doesn't it? There's 2569, there's 2503, so negative 25.558 falls in between those. So we've got the fourth position plus 20% of the difference between the fourth and the fifth position. All right, that is the 5% value at risk. Now the expected shortfall is a little bit different. In fact, it's more of a pessimistic view, and we'll see why in just a minute. But let's look at the expected shortfall. What we're going to do, again, with the same example, we need position 4.2. So what we're going to do is, let's take the worst value, which was negative 45.64. Plus, let's see, I'll do it differently. Plus a negative 41.03. Basically, we're going to average it. We're going to find the average of those last 4.2 positions. 33.49 plus 25.69. And that's negative, of course. Finally, so that's 1, 2, 3, 4. We want 20% of the next one. So we have 1 return, 2 returns, 3 returns, 4 returns, 0.2 returns. So we got 1, 2, 3, 4.2 returns divided by 4.2. And when we take this average, we get negative 35.92. So the 5% expected shortfall is this number, negative 35.92. The 5% value at risk was this number, which was negative 25.558. As you can see, the expected shortfall is more pessimistic. It's more negative. So really, what's the difference between these two? And the difference is that the 5% value at risk gives you the most optimistic outcome of the worst observations. I mean, you look at the very worst. You look at rank them from highest to lowest. The value at risk gives you the most optimistic of the worst. Whereas the expected shortfall doesn't. The expected shortfall averages the 4.2 worst outcomes. Hard to follow, perhaps. The value at risk gives you the 4.2 from the bottom. The 4.2 from the bottom is going to be higher, it's going to be a better outcome than anything that fell below it. Whereas the expected shortfall averages the worst 4.2. So it's going to be a more negative outcome than the value at risk will be. Crazy, huh? So we've looked now really at 5 different measures of risk. We've got standard deviation, which looks at all of the returns, all of them. Then we looked at semivariance. That doesn't look at all the returns. Semivariance only looks at the returns that fall below the average return. Then we looked at the lower partial standard deviation. It doesn't look at all the returns either. It only looks at the returns that gave us a return less than a risk-free asset. Then we moved on and we looked at the value at risk. Value at risk doesn't look at all of the returns either. It looks at it only looks at the returns at the very bottom of the distribution, but it gives us the best case scenario of the worst possible returns. And then the last one was the lower partial standard deviation, which again does not look at all the returns. It only looks at the returns at the lower end of the distribution, and it gives us an average of the worst returns. So kind of in order, we go from looking at all the returns to standard deviation, and as we move down the list from semivariance to lower partial to value at risk to expected shortfall, we go to the most negative place. Or I should say the more harsh definition of risk. Okay, so that's going to conclude what I'm planning to cover, that and also what I'd already covered, but what I'm going to include and want you to know from Chapter 5. Okay?